name is Thomas Papenbrock, and I'd like to welcome you here to the second day on the ECT STAR workshop on machine learning and quantum computing. So today we have two talks and two 30-minute talks followed by 15 minutes of discussion. And then actually we have, after the first talk, we have a break and we will start then at 5 p.m. Trento time with the second talk. Yeah. So our first speaker is, I'm sorry, and I would like to remind you all, so we are abiding by the code of conduct as it is posted on the website here. I invite you all to put your questions and comments into the chat box, yeah. Yeah, so basically I can summarize it as be respectful to each other. And we are looking forward now to Fianna's talk on machine learning for lattice field theory. Please go ahead.
Thank you very much. So it's a pleasure to be back virtually at the ECT STAR, and I'm pleased to give this talk. Okay, so as a brief introduction to the goals of lattice field theory, of course, the overarching aim is to understand hadron and nuclear structure and reactions from the standard model. We want to understand within the same framework the structure of the proton all the way to the structure of nuclei to understand how finely tuned nuclear complexity is, and also as background and benchmarks in searches for new physics. And so the main topic of this course is machine learning, but just as a, since this workshop's about many body physics particularly, I just wanted to briefly mention that theory studies of nuclei, of course, have enormous importance and impact in the context of many of the intensity frontier efforts searching for new physics that many of us are interested in. And so in the study of the standard model, so trying to make first principles studies of hadron and nuclear structure and reactions, the challenge is really in the strong interactions in quantum chromodynamics, which is of course non-perturbative at low energies. And so the only systematically improvable approach to studying this structure from first principles is via the lattice formulation, where QCD is discretized onto a four-dimensional space-time lattice. So then what you get is the path integral, the equations of QCD, become integrals over the values of the quark and gluon fields on each site or each link. And I'm emphasizing this because, of course, to understand how machine learning is applied, we need to understand the mathematical formulation. And so what this looks like mathematically is integrals over something like 10 to the 12 to 10 to the 15 variables for state-of-the-art calculation. So the entire approach is based around very high dimensional integrals, which we evaluate by importance sampling. Of course, the idea is very simple, that even just from a quantum mechanics perspective, we know that paths near the classical action dominate and other paths are less important in a very precise way governed by the exponential of the action. So we can sample the important paths relatively more with exactly the right importance weight. And then we can compute physics on a set or an ensemble of these samples of the quark and gluon fields that let us do the path integral. So to get just slightly more technical, of course, these calculations are done on a Euclidean spacetime with some finite lattice spacing and some finite lattice volume. And to recover QCD, you need to take the continuum limit as the lattice spacing becomes fine and the infinite volume limit as the box size becomes large. And so the calculation that I described just on the previous slide, but now written out in terms of the QCD path integral. So this expectation value of some operator, which looks like integrals over our quark and gluon fields, becomes within the lattice approach, this computation where we've got our field configuration. So our samples of these quark and gluon fields already distributed according to this exponential weighting of the action. And then the expectation value looks like the mean over these samples of the quantity of interest that we're computing. And what I want to emphasize is that lattice field theory is a systematically improvable approach that has the same free parameters of QCD itself. So the quark masses and the strong coupling. And then once those parameters have been fixed by the quark masses by matching to some measured hadron masses, and then you need one additional parameter, one additional experimental input to fix the lattice spacing and equivalently the strong coupling. Then everything else from details of the internal structure of the proton all the way up to nuclear structures and structure and reactions are predictions of the theory. And that this is really the crucial feature of lattice field theory. And so if we're thinking about machine learning for lattice field theory, this is where we have to be very careful. Machine learning is, of course, a class of tools for optimizing the parameters of very complex models to describe data. So in the context of lattice field theory, where the entire idea is that we're trying not to model, we're trying to do a first principles calculation that gives us, in a controlled way, QCD in all of the right limits, we have to rigorously account or correct for the effects of modeling in a provably exact and provably unbiased way, mathematically speaking. So what machine learning is not is any sort of a black box or any sort of a model independent solution to, for example, inverse problems or to any problem, because all it is a very complex model. Might be a very general model, but nevertheless gives complex models. So right now is a very challenging time for the lattice field theory community in the context of machine learning, because there are many efforts to try to apply machine learning with very different levels of sophistication. And without a fairly deep understanding of what's happening, it can be hard to tell whether all of these details, formal quantification and propagation of the effects of any modeling, are taken into account fully and rigorously. And so this is the great challenge, how to take machine learning applications in industry where provable correctness and exactness isn't always necessarily the goal. Often a model that does what you would like with some performance is sufficient, and turn that into something where we can show rigorously that we preserve all of the features we need from lattice field theory is really the challenge. So if we're thinking about the workflow of a lattice QTD calculation, primarily the goal is, of course, to accelerate these calculations. Lattice field theory takes something like 10% of open science supercomputing in the United States. And so to really grow beyond that scale, beyond what we can do with current resources, one of the most efficient ways is to improve the algorithms, to improve the efficiency of the calculations. So a lot of effort is, of course, directed at accelerating each step of the lattice QCD workflow. So in broad terms, the first step is to generate field configurations, which is currently done by our hybrid Monte Carlo or a Hamiltonian Monte Carlo approach. So this is an extremely computationally expensive step. This takes leadership class computing. It takes thousands of GPUs, tens of teraflop years. Ultimately, you want a fairly small set of these samples of field configurations, order thousands, but each is very large, something like 10 to 100 gigabytes. Then you have to evaluate the operators on each field configuration. You have to compute propagators. So this involves computationally large sparse matrix inversions. And then you have to contract into correlation functions, which is smaller scale computation, but it needs to be done very often. So this can be done on the scale of a few GPUs. And of course, in the context of many body physics, the computational cost grows exponentially and factorially in various of these steps with the size of the nuclear system. So those are exponentials and factorials we'd like to be able to overcome. So existing efforts to apply machine learning to lattice QTD really target various aspects of this workflow. So one of the places where machine learning efforts are most developed is at the first step of this workflow in field configuration generation. So I'll talk more about this in detail. It's what my group's been working on. Our papers are highlighted here in green, but also lots of lovely work from other groups. This has been targeted because it's really extremely computationally expensive. And so we have great hope of some ways of significantly accelerating this part of the workflow. And those approaches have ranged from things like multi-scale approaches, a lot of effort to accelerate hybrid Monte Carlo itself, through to direct sampling methods where we don't use hybrid Monte Carlo anymore at all, but try to design ways of directly sampling from the probability distribution of interest. Then there are nice efforts at efficient computation of correlation functions or observables given field configurations. So I should say that the field configuration generation is a really complicated problem. And so most of these efforts are still operating on toy theories, just starting to work on QTD themselves. Thinking about computations of correlation function and observe, typically these studies are already looking at QCD, but the potential for improvement is smaller. So typically advances here are so far not orders of magnitude acceleration, they're fractional accelerations. There's of course really nice significant efforts at sort of changing the lattice field theory prescription to avoid sign problems via contour deformation of path integrals. And so these approaches are now also using machine learning to find nice contours to deform. That's another exciting direction. And then there's of course not accelerating any of the standard parts of the lattice QCD workflow, but can you use lattice QCD in the analysis stage or to gain insights about your calculations? And here you don't necessarily need to be quite as mathematically rigorous because this is the interpretation stage, and there's a lot of nice work on that front as well. So as I've said, a lot of the approaches to accelerating lattice field theory or interpreting lattice field theory via machine learning are at this stage in a developmental stage. So many of the papers listed here use toy theories instead of QCD as stepping stones to the full problem. And if we're thinking about toy theories, there's also a lot more related work in, for example, the condensed matter context, which of course I haven't listed on this slide, but tackling many of the related and similar issues. So as well as this sort of overview of where machine learning is starting to impact lattice QCD, I want to dive a little bit into one of the most developed approaches in terms of configuration generation and give you an idea of sort of the status and prospects of that, an idea of the realities of the technical challenges involved. So that part of the lattice QCD workflow is sampling of field configurations. So mathematically, the problem is quite straightforward. You're trying to sample field configurations here from some known probability distribution given by the exponential of the action. And what these field configurations look like is something like 10 to the 10 links. So you can think of them as living here on these edges of your hypercubic lattice, encoded by SU3 matrices, so 3x3 complex matrices. And you want to sample these sets of links according to a known probability distribution given by the exponential of the QCD action. And you want order thousands of these samples. So what's traditionally done is a hybrid or Hamiltonian Monte Carlo approach where you're updating configurations. It's essentially, you take conjugate momenta from a Gaussian distribution at the start of the trajectory, then update the fields and momenta, this coupled position and momentum walk through Hamiltonian dynamics to explore the space, and then you do this again. And so this is updating your configurations in steps in a chain. And those configurations in that chain are correlated. And so then the amount of time to burn into your probability distribution and also to get independent configurations is dictated by the autocorrelation time in the chain. So how correlated the subsequent configurations are. And this is where one of the great challenges for this conventional approach comes from, is that the updates are close to local or they're diffusive. So if you want to update configurations on the relevant physical length scale, like the size of a proton or the size of a nucleus, then as the lattice spacing becomes fine, the number of updates you need to change physics on that fixed physical length scale diverges. And so this is critical slowing down in this context. Okay, so this is one of the big challenges through the generation of fine configurations with fine lattice spacings for lattice QCD calculations. And this is one of the reasons that machine learning approaches to this task are developing very rapidly. So to give you an idea of the application of machine learning, we can think about a scalar lattice field theory where everything's easy to visualize. So here you have a real number per site instead of 3x3 matrices on the links of a lattice. We have a simple action, here just the phi to the 4 theory action. And we want to generate field configurations with this known probability distribution given by the exponential of the action. And we can visualize the configurations just as these pictures, where each color, of course, tells us about the value on that side of the lattice. So we'd like to sample field configurations that are likely. So like these ones here, which come from this part of the log probability distribution that looks good. And not this is random noise. You can see that the correlation structures of this configuration are sort of different. This is just noise as opposed to having this sort of characteristic correlation scale of likely configurations. And so we'd like to sample configurations like this and much less often configurations like this. And Of course, this draws parallels to image generation problem, which has received a lot of attention in the machine learning community. So these are not pictures of people, these are machine generated images for machine learning algorithms trained to generate pictures of people. And so this is, of course, a really nice result. You can go to www.thispersondoesnotexist.com, and every time you refresh, there'll be a new machine generated picture. So if one can have a machine learning architecture that generates this and not this, you would think that maybe we can apply the same thing to generate this and not this. With, of course, the very crucial difference that here in the image generation problem, you never want pictures like this, which is just random noise. But in the context of lattice gauge fields, we do want this, just far, far less often than we want pictures like this. So, of course, the comparison between this sort of an image generation problem and the generation problem for ensembles of lattice gauge fields reveals a lot of the challenges. So each gauge field configuration is represented by something like 10 to the 9 to 10 to the 12 numbers. And ultimately, you want something like 1,000 samples. In a benchmark image set for machine learning, each image is represented by something like 3,000 numbers, but you have 60,000 samples that can be used for training. And so clearly we have an inverted data hierarchy here. The number of degrees of freedom per sample is far higher than the number of samples you might have available. So many of the sorts of training paradigms used in industry application of machine learning won't be able to be applied here. Moreover, for us, it's the ensemble that has meaning in a physical sense. It's long distance correlations that are important, as opposed to generating pictures of people. Each image has meaning in itself. Short distance structures like a nose or an eye have their own meaning in themselves. And so you can imagine that a lot of the architectures developed to solve the image problem won't necessarily directly apply to the lattice gauge theory problem. And then, of course, we have complicated symmetries, things like gauge invariance and translation invariance with periodic boundary conditions, which, of course, images don't have. So for solving the full QCD problem, it's quite clear that out-of-the-box machine learning tools aren't appropriate. And we're going to need custom machine learning for physics from the ground up. And so just a detailed example of one way that you can do this successfully is by developing so-called flow-based models, where the idea is very simple. You're trying to learn or optimize, it's just a model, you're trying to optimize the parameters of a model, a change of variables that takes you from an easily sampled distribution to the distribution of interest. And then if you can learn this change of variables in a way that's invertible and has a tractable Jacobian, so you know how the probability density flows, then you've solved your sampling problem. You can take samples from the easy distribution and put them into your function and outcome samples from the complicated distribution that you're trying to sample. So you can show that this can be done with an invertible model with a tractable Jacobian by composing many simple transformations to produce a very general function. And so in the case of images, there's a very nice way of seeing this. You can do what's known as real non-volume preserving flow models, where the idea is just to take half of the variables. So this is a checkerboard of our image or our scalar field configuration. You take half of the variables here, the green ones, and you just leave them alone in any one of these layers, these coupling layers that compose to form your model. You take the other half of the checkerboard and you transform it with arbitrary scaling and arbitrary translations, which can be parameterized by complicated neural networks. As long as those neural networks depend only on the untransformed half of the data, then what you have is a nice lower triangular Jacobian that can be easily computed. Okay, so this gives you a very nice complex model with many free parameters to optimize that has a computable, tractable Jacobian and is invertible. You can also train this without needing samples from your distribution. Since you know the target distribution up to normalization, you can write down a shifted Kullback-Leibler divergence, which is defined here, which is a measure of the difference between your distribution of interest, which is P, and your model distribution, P tilde. And you can write down this in a form such that you can get stochastic estimates of this difference between distributions only by sampling from the model distribution itself. So here P tilde is the model distribution, and you can compute this only knowing the action computed on your configuration and the model distribution P tilde drawing samples from the model. So you don't need training data. You can guarantee exactness by forming a Markov chain. So taking completely independent samples and then composing them into a chain and accept reject based on the previous sample in your chain. You can then have a complicated model with many free parameters to optimize, which is the machine learning practice. You can guarantee the exactness of your final distribution, and you can optimize this model without needing any samples from the distribution itself. So this is clearly an appealing approach to generating field configurations. And in the case of a scalar field theory, you can do this exactly like you would do it for images. You can apply all of the machine learning tools almost out of the box. So you can parameterize the flow using these real non-volume preserving coupling layers. You can train this by taking samples from the model, computing the loss, doing gradient descent. And then once you've trained the model, you can save it and sample from the model by taking embarrassingly parallel samples and composing them into a chain. And you can see that an approach like this applied to scalar field theory actually overcomes the critical slowing down. So on this slide, we have here tau int, that's the integrated autocorrelation time. So a measure of the correlation between steps in your chain, or a measure of the cost. And you can see that for hybrid Monte Carlo, you have this exponential divergence of this cost as you move from left to right along this plot, which is along a critical line. Similarly for local metropolis, so another conventional sampling approach, for these machine learned models, you have no growth. So you've traded critical slowing down for some upfront cost of training the model. But once you have the trained model, there's no more slowdown in sampling. So this is, of course, a nice idea of bringing some of these machine learning approaches that work for image generation to lattice field theory. But to really apply it to lattice field theory at scale, you need a number of new innovations. So you have to scale the number of dimensions and the number of degrees of freedom very large. But more importantly, you also need to develop methods for gauge theories. So the complications here, of course, become that in gauge field theories, your field configurations are represented by links here, encoded as matrices, like we saw before. And so these group valued fields don't live on the real line, which is what most machine learning algorithms are designed to handle, but they live on compact connected manifolds. And then the action is invariant under complicated group transformations, gauge symmetries on these gauge fields. So to address this, you really need to go back. You need to design flow architectures for compact connected manifolds in the first place. And then you have to incorporate symmetries. So here's some work from my group in collaboration with Google DeepMind, going back to the start and designing flow architectures on tori and spheres. So the simplest examples of compact connected manifolds. And this is, of course, relevant also to other problems, like robot arm positions are represented by angles at each joint, right, which live on compact connected manifolds. So going back and doing this from the ground up has other advantages. And then once you have sort of the basic structures, you still need to incorporate features. So like the symmetries of the theory, like gauge symmetries. And I want to just make a note that incorporating symmetries like this isn't actually essential for the correctness of your machine learned generated ensembles, because you can still guarantee exactness, correctness just by the accept reject steps when you compose your samples into a chain, but it's actually critical for being able to train these very high dimensional models at all. And so you can define a gauge equivariant flow if you have a symmetric prior distribution, so the original distribution that you sample from before putting your samples into your change of variables, and have each coupling layer be equivariant under the symmetry. So you need all transformations to commute through applications of the coupling layer. And I won't go into gory details in this overview talk, other than to say that there's been a lot of work to make things like this happen. And you can see some nice pictures which show illustrations of the types of really physics-specific machine learning architectures that have been developed to incorporate these sorts of features. And in doing this, you can also show that the same successes you see for scalar field theory also apply to gauge theories. So in a U1 field theory, you again see that you can significantly beat down this critical slowing down, again at the cost of upfront training of the model. So here's just an example showing a sampling of the topological charge. So this is basically the winding number of the gauge field. So the Itea-Singer index theorem tells you that it's quantized. It's a global quantity. When you see that this is sampling using hybrid Monte Carlo, it remains stuck in topological sectors. It's not exploring the whole space. A heat bath approach, so another conventional sampling approach, is similarly stuck compared to the flow-based models here in orange, which are just exploring the space very efficiently. So if you look at that another way in terms of this integrated autocorrelation time or a measure of cost, you can see that the machine learn model here, again, moving from left to right along a critical line, is orders of magnitude more efficient than conventional sampling approaches. Okay, so this is just one example of a success of the beginnings of applications of machine learning approaches to try to accelerate lattice field theory calculations. So this is an example of an efficient, exact machine learning algorithm, which you can use for UN and SUN lattice quantum field theory. And there's still significant work to scale to the state-of-the-art calculations, but it's extremely promising, especially if you can realize multiple orders of magnitude improvements in regions of interest. As I said, there's also, of course, interdisciplinary applications of all of this work. Gauge symmetries aren't common in many other areas, but of course there's condensed matter applications. But many of these ideas, going back to construct flow architectures on compact connected manifolds, have other applications, from robotics to molecular genetics and drug design. And of course, lattice field theory is a very computationally advanced subfield. And so to really make it work at scale requires significant joint software efforts. So this is also something my group's exploring to exploit and extend existing machine learning software frameworks to run on CPUs, GPUs, TPUs, that's tensor processing units, to get ready for exascale physics projects using machine learning for lattice field theory. So the outlook is really that machine learning accelerated algorithms have huge potential to enable first principles lattice QCD physics studies for hadron structure interactions and for nuclear structure and interactions. And I gave you this particular example of flow-based generations, which could enable fast, embarrassingly parallel sampling to give you high statistics calculations, give you efficient ways of parameter space exploration, so you don't need to have entirely new Markov chains for sampling different parameters. You can retune trained models, you can reduce storage challenges, but there's a lot of work still to be done. And so the real summary is that there's huge potential, but there's still caution required that machine learning can accelerate lattice field theory while preserving rigor, but often out-of-the-box tools aren't appropriate because we have different goals, of course, than many other applications of machine learning. And in particular, the need to rigorously and mathematically preserve the fact that you're doing a field theory calculation in all the appropriate limits. So I just want to finish by saying that this work and a lot of diverse related work is now living in the NSF AI Institute for Artificial Intelligence and Fundamental Interactions, centered in the Boston area. This is IFI, which has 20 physicists and 7 AI experts, and we've just closed our first round of applications for postdoctoral fellows. We'll have something like 7 fellows in a steady state. And the whole point of this institute is what I've been stressing. It's machine learning to incorporate the first principles, best practices, and domain knowledge from fundamental physics. So things like symmetries, conservation laws, scaling relations, limiting behaviors, and so on. And the entire goal of this institute is to develop this next generation of AI algorithms informed by and targeting theoretical physics and experimental physics. So the three aspects of our center are AI for theoretical physics. So this was really what I was talking about. And I'm the coordinator of this branch of our center. We also have AI for experimental physics, all tied together by our work in AI for foundational AI itself. So how can physics, AI squared stands here for artificial intelligence and fundamental interactions, ab initio AI squared. How can this ab initio AI tell us about foundational AI? And sort of our model of the center is here as a proton where our fellows are gluing together our different areas in theory, experiment, and foundational AI. Okay, thank you very much.
Thank you very much, Fiala, for this great talk. So please use the chat function to, good, we have a question here from David Scheich. Cluster algorithms cure critical slowing down for spin systems, but fail for gauge theories. Is there any nice story with machine learning? Why machine learning seems more generally applicable compared to cluster algorithms?
Yeah, so I mean, the machine learning approach I just described in some detail, the flow models, is completely general. You can use it for gauge theories without any problem. So like HMC or heat bath, it generalizes very easily.
Thank you. I also had a question, and basically I didn't get completely the gauge equivalent. Does this mean that the machine learning avoids to generate configurations that are connected by gauge symmetry or by trivial gauge transformations?
Yeah, so what it does is it guarantees that the probability of producing configurations connected by gauge transformations is identical. So it's it respects the gauge symmetry, which of course reduces your parameter space. And so then when you're trying to optimize the parameters of your complicated model, you've cut out that very high dimensional symmetry. So you're not trying to optimize along the flat direction of your parameter space. So you've basically reduced the dimensionality of the optimization problem, cutting out that gauge direction.
Thank you. Abhishek asked, where can we learn these flow-based GANs?
Yeah, so this was not a GAN. It wasn't a generative adversarial network. It was just a flow-based model without the adversarial part. Where can you learn them? So there's original papers from some people at Google DeepMind. There's my own group's work, and actually we're about to publish a tutorial notebook on how to on flow models for theory, but also for gauge theories. So that will be posted to the archive as an attachment to some of our earlier papers in the next month or so.
Anyone else, please, more questions? It seems you can also unmute yourself and ask directly.
So we have a question from Natalie here. She raised her hand.
Oh, please, go ahead.
Hey, Fiala.
Hey, Natalie.
So you showed that how an upfront cost attaining some type of trained model could lead to dramatic advantages. So I wanted to ask about your perspective on the cost of training these models and also of the cost of storing these trained models.
Yeah, so certainly the cost of storing is nothing to worry about at all. The models are reasonably compact to store, but more importantly, if you have a trained model, generating samples from it is very efficient. So then you can avoid storing samples, which are much larger. So you can think about replacing storing an entire ensemble of gauge fields or several ensembles, because you can also tweak the parameters of your model to look at different parameters with just a model. So storage, not at all a problem. Training, now training could be the sticking point. This is really the question. Are we going to be able to train these models at the scale of state-of-the-art calculations? So what we've found so far in our smaller scale studies is the first attempts to train a model, it takes a long time. It takes so long that you would perhaps think it's not worth it. But once you know how to train the model, then you can train them very efficiently. So the question is, are we going to be able to take our studies and learning on smaller scale models and successfully train a model on Aurora at state-of-the-art scale, or is that training going to be the bottleneck? And I don't know the answer to that right now. What I can say is that learning to train these models is, we're getting better and better at it, but it's sort of an experimental question at some level.
So when you say once you know how to train these models, it's very efficient, what's some of the know-how?
Yeah, so there's a whole range of things. So within the class of the gauge equivariant models, you can think about different structures. So something we've had a lot of success with is hierarchical models, where you can have essentially a hierarchical and convolutional structure that you can train on smaller lattice volumes to start, and then initialize your model for larger lattice volumes from that for smaller volumes. And you can get big accelerations like that. There's all of the simple hyperparameters in machine learning optimization. There's your learning rate, the batch sizes in your training algorithms. There's what sort of an optimizer you use to do your gradient descent. There's different things on the market. All of the free parameters those optimizers have. But I'd say at this stage, and I should also say for these, I showed an example for scalar field theory where you have this checkerboard masking pattern. Of course, this gets much more complicated for gauge field theories, and I didn't really show it, but you have a lot of choices in the masking patterns of updates, which of course, ideally you choose based on your understanding of the physics of how to best couple to represent the correlations in your data while still being able to guarantee exactness. But we're still really in the early days of which of these choices, even though all of them can ultimately give you the right answer, which ones are most efficient to optimize.
Interesting. Thanks, Phil.
We have two more questions. Vitek and Dean raised their hands. So, or maybe another one I did not see. Vitek, go ahead first, and Dean follow, please.
Okay. Hi, Fiala. Very nice talk. So, in the beginning of your talk, you mentioned the issues related to black box approach to machine learning, which of course raises the issues of interpretability. Okay. In this context, could you say something about uncertainty quantification of machine learning for lattice calculations?
Yeah, so I can. So what I can say is that there's a very big range of machine learning approaches for lattice, and in some of them, how you propagate uncertainties through the models is absolutely critical, and in others it's not. And what's needed is the ability to know the difference. So for example, in the flow-based models I showed, you can guarantee exactness through the accept reject step. And you can show mathematically that you can guarantee exactness based on certain properties of the model and the prior without trying to propagate any sort of uncertainties through the model at all, because you can compute exactly the density from the model. If you're trying to do something different, like predict some lattice field theory quantity from another lattice field theory quantity, suddenly it becomes absolutely critical to mathematically propagate the uncertainties of that prediction based on what data set you've used to optimize it, how you've used to optimize it, how generalized the model is, and the fact that you have a model that's not completely arbitrarily general through into the final result. So I would say that in the various different applications, at how and what uncertainty propagation means varies very widely. And it's, in my view, absolutely critical to only use machine learning for lattice field theory where you can prove rigorously that it is exact.
Okay, thank you.
So Fiala, so thank you very much for the really great talk. I learned a lot from that. So I wanted to ask you about sort of the real hard problem. Suppose you had a theory where you want to sample from important configurations that are disconnected. And let's suppose you have 15 disconnected manifolds and your training found 4 of them, but you didn't find the other 11. So how would you know that you made a mistake, that you have autocorrelations that are not sampling the other 11? How would you know that?
Yeah, so my first comment to that is that that is really hard. And of course, that is a failure of hybrid Monte Carlo too, that you can't at some level.
Yeah.
The advantages that you do have in machine learning are that because you're not updating, you don't get stuck. And so as long as your training, your initialization of your network has density everywhere, you're not going to miss modes at the outset. What can happen is that you can follow an optimization pathway that pushes you into a mode. So then there are various ways of trying to control for that and various ways of trying to check that. Trying to check that is, of course, you can do something that won't give you efficient samplers in the end, but you can push into localized areas of your final parameter space in like a grid search and see where you find density. And then look at your final trained model and compare, have you missed any of these peaks? So you can do things like this. You can add penalties to your loss term to assume, you start with density everywhere to penalize it for moving away from small densities to try to stop yourself from running to peaks. But I mean, the complete upfront answer is ultimately you can't, in the same way as you can't via any other sampling approach, but you do have some advantages over updating based methods in exploring that space. And so we're writing some work on this for multi-peak distributions, sort of trying to outline some best practices. But you sort of can't escape the reality that if you miss it, you miss it.
Okay, thank you.
Hi, Fiala, this is Alessandro. Thank you very much for the very nice talk. I have a question. So, I mean, maybe I misunderstood some of the points of your talk, but so here you developed an algorithm that basically allows you to do an almost perfect importance sampling that respects the gauge symmetries of the theory, so that all configurations that are just gauge transformation of the other are sampled with equal probability. And my question is, and that gives you, of course, a tremendous advantage in the importance sampling itself, and that helps you with the sign problem, I believe, by brute force in a sense. But can you combine this kind of technique with contour deformation so that you can actually sample an optical configuration that reduces as well the sign problem?
Yeah, so you can totally combine this tool with some of the really nice work that's happening in contour deformations. I mean, essentially the sampling approach that I described, if you can define the probability distribution that you're trying to sample from, whatever that is, you can try to train these sorts of a model. So you can combine it with contour deformation approaches, both where you're trying to change your sampling of the gauge fields and where you're trying to change your computation of the observables.
Okay, thanks.
Another question in the chat from Chinmay Mishra, who asked, are you by any chance planning on making these trained models available at a repository somewhere?
Yeah, so I mentioned earlier that we're going to put out a tutorial notebook, which that will include some trained models with it. And also, of course, it will go through, a Jupyter notebook, how to train them, etc., for some small scale systems. For larger scale things, the ultimate goal is if we can make this work for QCD, of course, we'll make the trained models available widely to provide efficient configuration generation is the ultimate goal. For the existing papers published on U1 models, if someone has interest in them, let me know and we're happy to share them, but they're not published anywhere because at this stage they're primarily toys or proofs of principle. But if you've got a use for them, please reach out.
Are there any more questions, comments? Okay, I would say, well, thank you to all questions and questionnaires and people who commented in the chat, and thank you very much to Fiala Shanahan for this very inspiring talk. I would say we take a 15-minute break about now, and we reconvene on the hour for Zorel Davoudi's presentation. See you soon again. Okay, welcome back everyone to the second half of our today's program. And speaker is Zorida Woody, and she will talk about nuclear physics entering a quantum simulation era. Lessons from the past, vision for the future. Please go ahead.
Thank you very much. Thanks for this great opportunity to talk at this very interesting workshop. So I'm going to talk a little bit about this topic of quantum simulation for nuclear physics, trying to convey some of the excitements and progress in this field, and hopefully give some views of what the future might look like for this field. I've kind of given a similar talk at the DNP meeting a few days ago, so apologies to those who've already seen the talk. Hopefully there are some slight new things in this talk for them as well. So with that being said, let me move to the motivation for the talk. So let me say a few words about what we mean by quantum simulation for nuclear physics and what it actually implies. So in this context, we're actually thinking about, in general, for quantum simulations, to leverage a quantum system that can be controlled in the laboratory to study another quantum system that is more elusive, whether experimentally or computationally. So for nuclear physics, we're probably thinking about maybe starting from quark and gluons and the standard model degrees of freedom up down here. And then these we know are the fundamental building blocks of a nucleon. And the nucleon is building the atomic nucleus. And the nucleus itself is sitting at the core of the atoms, which are making the molecules, and these are making the materials. And maybe we can also think in this context of more microscopic and large systems like those relevant for astrophysics context in this picture, the neutron stars. And what we mean by quantum simulation is to be able to actually study and make predictions for systems in nuclear physics, this part of the diagram, by leveraging systems in atomic or condensed matter contexts that are of fundamentally different sizes and scales and effective degrees of freedom, and then be able to study the systems that we're interested in, maybe eventually also something like neutron stars. And in this context, we're thinking about whether doing this using these quantum systems and quantum materials that are used in a digital quantum computer, or in a more kind of natural way as an analog simulators of these systems. So let's see how that works. Well, of course, this seems to be the right time to start thinking about this problem. And this is because there are a range of quantum simulators out there with varying capacity and capability that are available to researchers. These are whether at the universities or the companies, and then eventually, hopefully, at the national labs in the US and in other countries. And therefore, that's the reason for a lot of excitement that we should start thinking about how to leverage these systems as they move into the future and becoming more complex and more capable. All right, so I want to declare that this is not possible to convey all the excitements and progress in this topic in 30 minutes. I'd be happy to deliver a few messages, and therefore this would be somewhat scattered, but hopefully not random review of the literature. And along the way, I want to make a few points, and I want to sort of make sort of a few observations or a few viewpoints of what we should be doing in the future to really push this field forwards. So again, apologies to many whose work will not be properly covered. This is a very fast-moving field, and there are a lot of scenarios and ideas that you can imagine. I would only constrain to give one or two examples for each of these points that I want to make. And these are sort of the summary of those points. I want to go through them one by one. And as I said, make an example or two of what I mean by that message. So the first is, of course, we know that nuclear physics is not short of hard computational problems. Fiala very nicely already described one of these hard computational problems for us, and the way that we can still leverage classical computing algorithms to speed them up. So we also now think in this context, maybe quantum simulation can help us move forward. But there's much to be done to really change the game in computational nuclear physics when it comes to using quantum technologies. So the nuclear physics motivation for leveraging quantum technologies I can sort of sort them into important categories. We would like to study nuclear isotopes, dense matter, and fundamentally the phase diagram of strong interactions or QCD, because as we know, with our current computational technologies, lattice QCD or ab initio nuclear many-body methods, we've been limited by the sign problem with finite chemical potential for fermionic systems, or with a signal to noise problem if you think about a finite density system. Another set of problems that we'd like to address, and we've been very much limited with the current technologies, is the real-time dynamic of matter. For example, how the matter evolves after the collision of the heavy ions or after the Big Bang, right? And in general, any observable whose definition depends on the Minkowski signature of a spacetime, for example, a wealth of dynamical response functions, transport properties, hadron distribution functions, and a lot of interesting physics that we're probably missing by not studying non-equilibrium QCD, but is important, as I said, for understanding the evolution of matter after extreme conditions. So again, we have been limited by the sign problem, and we would like to avoid this by leveraging quantum simulation and quantum technologies. So the next message is that in the same way that in classical computing, we've been cleverly defining the appropriate degrees of freedom of the system, given the physics that we are interested in, we have to approach these kind of problems with quantum simulation the same way. So identify the degrees of freedom, whether we're interested to start from the QCD degrees of freedom or nucleonic, or maybe macroscopic or hydrodynamical degrees of freedom. And then along the way, find the most efficient mappings of these degrees of freedom and their interactions to the quantum hardware. So what do I mean by this? So of course, this is sort of the map in a sort of low energy or first principle nuclear physics that we are hoping to really achieve with computational nuclear physics, right? And a lot of us in this crowd are being involved in various steps of this program. And this is a matching program that starts from first principle calculations based in QCD using, for example, lattice gauge theory methods, trying to constrain physics at the multi-nucleon level, and then using that constraint to constrain the effective field theories of these interactions and responses to then feed them into the many-body nuclear structure and reaction calculations. And then these can start making predictions or reliable and systematic predictions for a range of very interesting questions that we're interested in many-body nuclear physics, right? So then now the path for quantum simulation looks like to be, we can again either start from the standard model and leverage quantum technologies to maybe constrain effective field theories, or if you have capable machines, you may be able to address quantum in many-body physics, or you can start again from the ab initio nuclear many-body calculations and speed those up using the quantum hardware and quantum computing to again get to the problems that you're interested in. So again, simplifying this roadmap, what we have in mind is kind of two separate paths, either starting from a standard model interactions and using quantum technologies to fix EFDs or get to the physics, or start from the many-body nuclear calculations that's being constrained, have constrained EFD Hamiltonians, and then use the quantum technologies to solve the quantum many-body problem and get to physics. So have this in mind that this is sort of the path. So I want to give examples of each of these paths from the progress that has been going in the community in the past couple of years. The first example is the quantum simulation in nuclear structure and reaction. So what you see on the left is an example of a dynamical response function that is needed for neutron nucleus scattering. And in this case, Alessandro, Joe Carlson, and Joe Carlson have introduced a quantum algorithm that can compute the response function. For example, in the case of a simple Fermi-Hubbard model, they've demonstrated that this algorithm can actually accurately describe this, the theory predictions for this dynamical response function, which is quite nice. So I'm sure Alessandro will talk about this in this program. Another example that I think is kind of interesting is a toy model of a thermal neutron proton capture, MPD gamma. And again, Alessandro and collaborators have been developing algorithms to actually look at the transition probability for this sort of simplified picture of this reaction using different types of algorithms for estimating the sort of preparations of this state that is required for this computation using this excitation operator, which is just basically the magnetic moment. And these are the computations that are performed on the actual device. And in this case, this is an IBM quantum hardware. And using some noise mitigation technique, you can actually find agreement with the prediction. So these are quite encouraging, nice progress. There's been also some interesting quantum algorithms proposed for looking into parton distribution functions or structure functions from the perspective of quantum field theory. And I encourage you to check out these papers if you're interested in this topic. Let me give you another example from nuclear astrophysics. So in this case, we know that the collective neutrino oscillations are relevant for example, core collapse supernovae or neutron star mergers. However, this is a very hard computational problem. It's a very complex quantum many-body problem to solve. And if you want the detail of how to map out this problem into a quantum hardware, you can talk again to Alessandro, Joe, and collaborators. But what I want to emphasize is that so far, the classical computations of this problem have used a mean field approximation, which basically tries to ensure that you reduce the exponential size of the Hilbert space to a polynomial in the size of the system or the number of neutrinos considered. But however, there's a problem, and as shown in this paper by Servia and collaborators, if you look at the measurements of the quantum entanglements of this multi-neutrino system, and you just solve the problem exactly, you'll find out that the entanglement entropy as a function of the number of neutrinos actually grows. And with mean field approximation, you're actually working in zero entanglement entropy approximation. So that already tells you that this approximation, this classical simulation might be actually missing some important physics, some important quantum correlations in the system. So this is an example of why we need the quantum simulation in this problem. And of course, again, there's been ongoing work on trying to map out a small instance of this system to quantum hardware and demonstrate that this is really the path forward. So what about quantum simulations of quantum field theories, the other path that I mentioned? Now you can start with and use quantum hardware to simulate the theory from first principles. And similar to the other path, there's going to be several different developments that have to happen at the same time. And these involve theory developments, algorithmic developments, and also implementation and benchmark, which is really going to be an important aspect of all these developments. We have to see how our ideas and proposals work out on an actual hardware, and that would allow us to improve and maybe become more realistic, right? So let me give you an example of implementation and benchmark. There are a number of very interesting work on quantum simulation of lattice Schwinger model. This is one-dimensional quantum electrodynamics, the simplest gauge theory that you can think of that has a lot of features that we see in QCD. So it's a good model to start with. And really a lot of excitements in this field started from these computations by Innsbruck group of a 4 staggered side lattice Schwinger model. And this is sort of observable that is dynamical, tells you how many pairs of particle-antiparticle you produce out of the vacuum or zero particle antiparticle state as you evolve in time, right? This was done on a trapped ion 4-qubit system and already really a nice achievement at the time in 2016. This work was also implemented on superconducting circuits of the IBM by Martin and Natalie and collaborators at Oak Ridge and Thomas and others, where they actually use the symmetries of the system to simplify the problem farther so they can embed it in just 2 qubits. So the same dynamics, the same theory, but only on 2-qubit system. And therefore, they can achieve far more simulation time with this method. And we've been also benchmarking the same model on a trapped ion digital quantum computers that exist in Maryland. And because of the nice features of the system, we've been able to actually reach far longer simulation times than was possible before with other systems. There's also this nice work again by Martin and Natalie and collaborators at Oak Ridge, where they also look at the potential between the static charges in the lattice Schrödinger model. And the reason it's kind of an interesting example, it kind of fits in that picture of the matching of lattice QCD to effective field theories, because in this model of Schrödinger model, you can think about starting from fundamental interactions and getting the sort of energy eigenvalues of the system to fix the sort of the two-body and three-body interactions, and then maybe use them to make predictions for multi-body interactions. This is really sort of the path forward that we're hoping that the quantum computing and quantum simulation would facilitate in the upcoming years. There's been also quite a lot of progress on the analog side. Here is where you don't digitize the evolution time, and you just engineer the Hamiltonian of your system to mimic the Hamiltonian of the target system that you're interested in. The example that I'm showing here is a realization of lattice Schrödinger model within the quantum link model approximation of this theory with the cold atoms and trapping potential. In this case, they use two different types of atoms in the same trapping potential to really engineer all the different transitions that are happening in the building block of a lattice gauge theory, the two-side one-link theory. And this is sort of the experimental observation of all those evolutions of the function of time. And this is really exciting. And then in the next step, I imagine, and I think that Philip Haag from Trento was involved in this work. And presumably the next step is to really scale up the system and be able to make the correlations between the different trapping potentials. And so let me also tell you a little bit about what I mean by theory developments in this context. And that would be an example of a non-abelian lattice gauge theory. So Hamiltonian formulation is really the most natural path for quantum simulation as we know. However, there are some subtleties with the Hamiltonian formulation of lattice gauge theories, and that's because once you're in a Hamiltonian picture, then you have to ensure that you impose your constant of motions or your Gauss's law in the Hilbert space of the theory. And this is given by a local constraint, of course, and for non-abelian gauge theories, this is a complicated nonlinear sort of condition that you have to impose. And what that means is that if you look at the exponential large Hilbert space of the theory, only very small, exponentially small part of it is physical. So you might want to become more clever about how to redefine this theory so you don't have to deal with a large sector of the theory that is irrelevant for physics purposes, right? And let me give you an example of why this is important. This is for SU2 gauge theory in 1+1 dimension. And of course, the size of the Hilbert space would grow exponentially with the number of sites or the volume of the system with some coefficient. And what we've looked at is the growth of this coefficient as a function of the cutoff that you put on the gauge degrees of freedom, because these are bosons and you have to digitize them and put a cutoff on their degrees of freedom. And you can see that this actually become a fixed number for the physical Hilbert space where the Gauss's law is imposed, but it grows logarithmically with lambda for the full Hilbert space. So even for a small cutoffs, we're talking about hundreds of orders of magnitude of difference between the size of the Hilbert space when the physical constraints are imposed or they are not imposed, and you just look at naively the Hilbert space. So how do we deal with this problem from the theoretical perspective? Well, there are two paths really. I mean, one is that you start from just locally gauge invariant building blocks. So you reformulate your Hamiltonian Hilbert space in terms of degrees of freedom that are already satisfying that Gauss's law and are physical. And the formulation for SU2 is actually called loop string hadron, and the name comes from those physical building blocks and been developed by Indrakshin and Jesse Stryker and you can look at this publication. I'm not going to say too much about this. This is a really nice framework because it allows you to efficiently build up your Hilbert space, no matter what the dimensionality is. And it can be generalized to SUN. So I think this is really a path forward for dealing with this problem of not having to deal with non-gauge invariant Hilbert space. You can imagine another path where you have the same Hamiltonian and the same Hilbert space, but you try to suppress the gauge symmetry violations in the implementation. And I want to mention an example that is kind of recent by, again, Philip Hack from Trento and collaborators. When they imposed, they proposed this procedure where you add to the Hamiltonian a term that is proportional to the Gauss's law operator itself. So for this gauge theories, it's actually going to be single body operators. There's not going to be sort of entangling operation involved, and therefore it's a simple procedure. And there is a coefficient for this term in the Hamiltonian that is said to be very large. And by doing so, you can actually, by orders of magnitude, suppress the gauge invariant, the gauge symmetry violations in the implementation. And in this case, it's an analog setup, I think, and you can do this in a digital setup as well, and sort of this blue line. And you can ask me later what these other plots are, but sort of is the demonstration that you can actually suppress those gauge non-invariant dynamics by using this trick. And there are similar tricks for symmetry protections in the papers that I've listed below, so make sure to check them out if you're interested in this particular problem. All right, so what about algorithmic development? What exactly I mean by that? Well, if you think about the scalar field theories, for example, then this is an example from, again, Martin Natalie's paper on digitization of the scalar fields. And again, because we're talking about the scalar fields, we have to digitize them and we have to put a cutoff on sort of the whatever Hilbert space, however we define it. And here it turned out that the implementation and the efficiency of the implementation really depends on the basis of states that you pick. For example, in the Jordan-Lee Presskill, which is the field space sort of digitization of the field as opposed to harmonic oscillators, there are differences in the efficiency of the algorithms. But one thing that I want to emphasize is that, for example, this harmonic oscillator base is just with a few qubits, you can get exponential accuracy in the simulations that you perform. And therefore, you don't have to worry much about this finite cutoff that you put in this scalar field theory. And that seems to be consistent with what we observe also in the SU2 gauge theory coupled to matter. When you look at the low energy excitations of the theory, there's an exponential convergence to the exact value as a function of this cutoff on the gauge degrees of freedom. So this is quite encouraging and promising because it tells you that sort of the naive way of really putting a cutoff on excitations of these bosons seems to not really destroy much of the physics, but there are some subtleties there as well, you can ask me. This is an example from the Lattice-Schwinger model. I don't want to go through this because of the time, but you can look up in this paper, which is really a very comprehensive approach to identifying the quantum resource requirements for digital computation of Lattice-Schwinger model in near term and in far term. All right, so the next point that I want to make is that nuclear physics problems are different from condensed matter and quantum chemistry problems. However, we can learn still a lot from the progress in those areas, but we also need to think about new strategies and ideas to implement in nuclear physics. What do I mean by that? Well, let me tell you a little bit about the differences. So if you start from this path of going from nucleonic degrees of freedom and simulating nuclear Hamiltonian, well, now we are dealing with more complex Hamiltonian compared to an electronic system. The Hamiltonian itself probably is not known with arbitrary accuracy and precision. There are short, intermediate, and long-range interactions. There are 3 and multi-body interactions in dense systems. And at higher energies, you have to think about pions and other hadrons that can become dynamical. So we have to account for them in the simulation. If you start from a standard model, so the other path, then it's even more different from the quantum chemistry problems, because now we have both bosonic and fermionic degrees of freedom that are dynamical and coupled. And more importantly, we have both global and local gauge symmetries. And essentially, these systems are also relativistic, so the particle number is not conserved. And also the vacuum state itself might not be quite trivial, right, in the strongly interacting theories. There are some ideas and papers out there how to really cast this problem in a form that is closer to quantum chemistry and non-relativistic systems. So I encourage you to check out these papers. So this is an example from the analog simulations where there are proposals for how to perform a quantum chemistry problem in an analog sense using three-dimensional trapped ion systems in optical lattices. And in this case, the hard part is really engineering these long-range interactions or Coulomb interactions between the electrons. And there is this nice proposal by Peter Zolar and collaborators, which is already challenging. And if you ask experimentalists, they will tell you that this is still far away from being practical. Now imagine if you want to do this problem for the nuclear Hamiltonian, where instead of just the Coulomb interactions, we have a more complicated interactions, or in the language of effective field theories, we have to deal with multi-body interactions and also the pion exchanges and non-analyticities, then it's a much more non-trivial problem. So we have to start thinking hard about how to really extend and go beyond proposals that exist for quantum chemistry. In a digital setting, there are still, the digital means that you have to digitize the time evolution operator. And this is basically done usually with the Trotter-Suzuki expansion of the time evolution operator. However, this is not quite efficient necessarily for all sorts of problems. And there's been quite a lot of progress out there for looking into the more efficient algorithms for doing this digitization of the, or digitalization of the time evolution operator for different systems, given the structure of interactions. And as far as I know, there hasn't been any such comprehensive scaling studies performed for nuclear physics Hamiltonian. This is one of the areas that I think would see a lot of progress and excitement in the upcoming years for nuclear physics. There's another aspect which concerns the fermionic mapping, and in nuclear physics, of course, we have the fermions in 3 dimensions. And again, there's been a lot of progress of how to make these non-local fermionic mappings to become more local, and maybe even use the gauge symmetries and gauge groups to facilitate this. However, again, there hasn't been a complete study of the most efficient fermionic mapping given the structure of the nuclear Hamiltonian. This is another area that I think is going to see a lot of progress in the upcoming years. So very quickly, in a couple of minutes, I'm going to go through the last point. So I'm going to skip some of these examples. So one is the theory, the fact that I think the theory experiment development, co-development is really a key to progress. And maybe nuclear physics can impact the development of the hardware in the upcoming years, right? So what do I mean by that? An example is from the world of analog simulations with trapped ions that I've been pretty much involved with. And so here you can use a simple setup with sort of 2 global beams to address a set of ions that are sitting in a confining potential. And with this sort of simple setup, you can actually effectively sort of engineer an Ising Hamiltonian, and therefore be able to look at the long-range Ising spin-to-spin interactions, and maybe even look at the dynamical phase transition as this in this example for systems that you cannot really do this classically anymore. So this is quite exciting. Now you can sort of augment this setup with a set of individual beams that are addressing these ions separately. And if you have such a setup, then you can make this system to be a digital computer. So in terms of a universal set of gates, you can perform any quantum simulation on this hardware. And this is an example, again, by the collaboration between Oak Ridge and University of Maryland, when you look at the variational quantum eigensolver for finding the deuteron binding energy. Something that we actually worked out with experimentalists was that for analog simulations of the models that we are interested in, high energy and nuclear physics, we need more capabilities. And this is an example of enhancing the systems that they have to actually be able to simulate and engineer a Heisenberg model with flexibility over all these coefficients. And as we show, we can now have a setup that simulates the Schrödinger model or all sorts of gauge theories, even in 2 dimensions, by this enhanced setup. And now you can imagine you can really extend this toolkit, which is something that we're working on, to go beyond even the simple models that I've mentioned here, and see what happens. So this is really exciting, and I think it has to happen in many different platforms and through this theory experiment collaborations. We have to leverage both analog and digital simulations at the same time, and maybe reduce the time to solution in near term. This is an example I'm not going to go through because I think there's going to be a nice talk by Kyle later in the program where he's going to tell us how you can simulate the nuclear problem using a setup that is kind of an analog digital hybrid setup. And this is a work done at Livermore, also with collaboration with Francesco at Trento. Another important point is that we have to make sure to leverage also the classical computing capabilities that we have and think about hybrid classical quantum simulations. And maybe even quantum means can help us to develop better classical algorithms. I have a couple of examples here, and it seems like I'm running out of time. So I'm not going to go through all of them. One is the variational quantum Monte Carlo. And of course, the very first example of this for nuclear physics applications that generated a lot of excitement was a VQE applied to the deuteron problem on an IBM device. And the example that I'm showing in this slide is for the Schrödinger model that came out of the Innsbruck group. And another example that I tell you a few words about it is this idea that you can use your quantum or classical resources to simplify the quantum simulation. For example, the state preparation, this is really costly sometimes for quantum simulation. You can use your quantum Monte Carlo method in problems that there is no signal or signal to noise or sign problem to prepare that initial state, but then sort of feed that initial state to your quantum processor and perform the time evolution that is actually hard on the quantum hardware. And there's this nice example in this paper by Henry Lamb and collaborators where they demonstrate this in the case of a gauge theory. There's another interesting work actually by Fiala and collaborators when they kind of have a similar approach in the sense that you can use the quantum hardware now in using a variational approach to optimize the operators that you would then use in, for example, your lattice gauge theory calculations to get better overlap to the states that you'd like. So you can facilitate that part by using a quantum processor. And this is an example that they worked out for the case of the Schrödinger model. There's some words I want to say about tensor networks, but I skipped this. There's important connections here with the hybrid classical quantum computations, but let me just move on and just say just in a minute that, yes.
We're already a few minutes in discussion time.
Oh, okay. I'll finish in 1 minute. So I'll skip this message, just say that there's also possibility that we discover deeper connections in nuclear phenomenology by these quantum information tools. And maybe also the prototypes and simple models can provide insight before we are able to actually simulate QCD. The examples I wanted to show, and I will not go through them, was regarding the quantum entanglement in low energy scattering in nuclear physics, as well as these spin models of maybe as prototypes of QCD, where they show some confining potential just like in QCD, and maybe we could learn some lessons from these. And the last word is really the fact that over the next decades, we're going to witness a new ecosystem, quantum skillful nuclear physics workforce, and a lot of interdisciplinary collaborations that didn't exist before. And the reason for that is at least like just an evidence for that. In the US, there's lots of activities. And in fact, they've been ramped up into 2020 by the funding in nuclear physics for the universities and national laboratories to explore applications of QIS in nuclear physics. But of course, the huge investment by the Department of Energy on these national quantum initiative centers, there are 5 of them now established at the national laboratories, And I want to say that nuclear physicists are really contributing greatly to these programs. And in fact, David Dean, a nuclear physicist, is the director of one of these centers at Oak Ridge. And really last slide and last example, I think that this kind of workforce development in QIS and nuclear physics has already started. If I look around in University of Maryland and my team, I see that nuclear physicists are talking all the time to condensed matter physicists, AMO theorists and experimentalists, and also the experts in QIS and computer science side of things. And this is a very active and exciting time for all these junior scientists as well as senior scientists to learn from each other and really establish something interesting and valuable for nuclear physics in QIS. And with that, thank you very much.
Thank you very much, Zoe. So it was a very nice and extensive overview. So please, I'm sure there are questions and comments. Either raise your hands or ask questions in the chat box. While we're waiting for that, maybe I could start. You presented some overview also about progress in Hamiltonian formulations. And I wonder, so this would of course also benefit classical computing. So somehow, do we have now, not only the light front, but there are Hamiltonians now available that people could use to consider QCD solutions on classical computers as well?
Absolutely, this is a really good point. And in fact, this is one of the things that we've emphasized in kind of our recent paper on the Hamiltonian or efficient formulations for Hamiltonian simulations. We were only considering the classical Hamiltonian simulations. And the idea was that the motivation to start with was that we want an efficient formulation for quantum simulation, but it ended up being that if you actually find that efficient formulations, you're already exponentially reducing the amount of computation that you have to do on the classical side as well, right? So this is really crucial. And there are progress also in tensor networks that I didn't mention, right? Now, if you merge these efficient formulations with tensor network strategies to avoid exact diagonalization and have more clever ways of going about the quantum Hamiltonian computations on a classical device, then you can gain a lot of benefit there as well. So yes, exactly. I think that's true.
Thank you. And maybe another follow on simply. So are there also, so I'm aware about the Hamiltonian formulation in that sense that I could do time evolution with a Hamiltonian, but you also showed clearly e to the s is also, or e to the is is in Minkowski space. So are there somehow in that sense action-based proposals for solutions to quantum field theories?
So that's a good question. If there is, I'm not aware of, but someone can correct me. And one thing that you can notice is that, as I said, these hybrid classical quantum algorithms now could allow you to perform your action-based simulation. I mean, we do a lot of things very well nowadays with lattice QCD methods. Why do you want to completely toss it away and just do quantum simulations from beginning to end, especially near term when we don't have enough quantum resources, right? So you can think about just keeping your action-based simulations, but the parts that are suffering from signal to noise problem or sign problem, as I showed in those two examples, you can replace them with the quantum processing step, right? So yes.
Thank you. Any other comments, please? Please use the chat or raise your hand. Okay, then I would say then thank you again, Zoe. Thank you, Fiala, for this great second day. And I would say so, see you all again tomorrow. And yeah, have a good rest of the day or have a good night, wherever you are. Bye-bye.